Okay, welcome to part 3 of the day 1 opium lecture series. Now we'll move into pain perception, what it is and how it works. Um, we can divide pain into at least two different categories. There's acute pain, which is going to be short acting and biologically useful. These are the cues that tell you to move your hand away from a hot stove. Um, we can compare that to chronic pain, which is going to be much longer lasting and cannot be due to a secondary condition such as cancer. Some examples that you're all familiar with are going to be back pain and migraine, arthritis, etc. Now, these different types of pain are going to rely on different mechanisms, which we'll go into. So remember, opioids inhibit neural activity. So we're going to look at why, in particular, decreasing neural activity in these regions with high opioid receptor density results in an analgesic effect in pain reduction. So let's start at the peripheral nervous system and look at the receptors that are responsible for transducing a painful stimulus into a signal that gets transmitted to the brain. So nociceptors are basically bare dendrites, free nerve endings that are going to depolarize after a painful stimulus. There are different types of receptors that respond to different types of painful stimuli, such as heat or cold or tear or stretch. Now, the speed of transmission is going to depend on the type of nociceptor and specifically whether they're myelinated or unmyelinated. Remember that myelination is like insulation that surrounds the axon and can dramatically increase the transmission speed of the neuron. So early painful stimulus for an acute type of pain is going to be mediated by these myelinated fibers. They're called the A delta neurons. And these are going to conduct action potentials rapidly through saltatory conduction along the axon. Slower nociceptors are going to have unmyelinated fibers, and transmission is going to be much slower. And it's these receptors that are associated with the emotional component of pain. So the early or acute pain is going to be mediated by those myelinated A delta neurons, and it's going to result in an immediate sharp sensation of pain. So we can compare that to the secondary or late pain, which is going to be mediated through those unmyelinated axons. And that's going to result in a slow, dull ache, and it's going to be more highly associated with the emotional response to pain. And you can see on the diagram on the right-hand side, pain intensity versus time. So upon receiving that noxious stimuli, the A delta fibers are going to respond first due to their faster transmission. So you'll see a sharp peak of pain intensity followed by cessation, and the onset of the second or late pain response due to those unmyelinated fibers. So how big of an effect does myelination have on neural transmission speeds? On the diagram on the right-hand side, you can see speed is recorded in miles per hour. We can compare different nerve fibers to things like walking or a bicycle or an airplane, just to get an intuition about how fast these neurons can transmit information. So the C nerve fiber is, remember, the unmyelinated axon, which we expect to be much slower than the myelinated versions. So the C nerve fiber is just a couple miles per hour slower than walking, for example. The myelinated neurons, the A delta nerve fiber and the A beta fiber, are at 50 and 200 miles per hour, respectively. And this explains why we get different types of pain response of acute versus more dull, long pain response. Okay, so let's look at some basic neural circuitry for pain transmission. On the diagram on the right-hand side, you can see the red is the unmyelinated C fibers, and in blue are the alpha delta fibers. These are the faster myelinated neurons, and that's what we want to look at first. So let's follow that path. Let's say we have some incoming pain from the periphery in the nociceptors. That information travels into the spinal cord and quickly crosses to the opposite side. That information is then relayed up through the medulla and pons of the brainstem into the thalamus, where it's then again relayed up to the cortex for some more complex cognitive operations like sensory discrimination and localization of pain and recognizing pain. Okay, so now let's take a look at late pain transmission through the C fibers, the unmyelinated, slower C fibers in red. We'll have the same starting point. We'll have signal transduction through nociceptors in the periphery. That information is transmitted into the spinal cord and quickly crosses sides. That information is then relayed through to the thalamus, except this time we're going to take a pit stop at the periaqueductal gray. And remember, the density of opioid receptors and opioid-producing neurons is highest in the periaqueductal gray matter. So the periaqueductal gray sends information back to the brainstem for descending control and reduction of pain through those opioid-producing neurons. The activity at the periaqueductal gray is further modulated from higher order inputs like the frontal cortex and the amygdala. And there are thalamic projections to limbic regions like the anterior cingulate and nucleus accumbens that are mediating the emotional component of pain, the emotional response. Okay, so now let's put it all together. We've seen that opioids decrease and inhibit neural activity through at least 3 different mechanisms. We talked about postsynaptic inhibition, axoaxonic, and presynaptic autoreceptors. All decrease the firing rate and hyperpolarize neurons and make them less likely to fire. We also saw where those opioid-producing neurons are most concentrated in the brain and some basic neurocircuitry of how that pain response is mediated and routed through the brainstem and the periaqueductal gray for control. So now let's see how that system works together to modulate the pain response. So opioids work by reducing neural activity in key locations, such as the periaqueductal gray. You can see here in yellow or orange the descending pathways that act on the spinal cord to inhibit the pain response. And we'll talk about 3 different ways that that can happen in the upcoming slide. And we can also reduce neural activity in the final target locations, such as the cingulate cortex. So I've stressed that the density of opioid receptors and opioid-producing neurons is very high in the periaqueductal gray matter, and that descending fibers from the periaqueductal gray into the brainstem modulates the pain response. There's strong evidence that electrical stimulation of the periaqueductal gray results in strong analgesia. Moreover, the periaqueductal gray projects to the raphe nucleus, which we've talked about in the context of serotonin, as well as the locus coeruleus, and those projections can also reduce the pain response. Okay, so let's take a look at those 3 different mechanisms by which descending projections from the periaqueductal gray can modulate the pain response. So we have 3 different diagrams we're going to look at. Let's start with A in the upper left-hand corner. You can see the descending inhibitory pathway that's coming from the periaqueductal gray. And you can also see on the end here the free nerve endings. These are the nociceptors where the noxious stimuli is incoming. It's transduced into an electrical signal. It transmits through the axon towards the projection neuron. Now, if there's no inhibition through the periaqueductal gray descending pathways, then we'll have a pain response. But that inhibitory pathway can shut down that projection neuron to overcome the excitation, to inhibit that excitation from the nociceptor to inhibit the pain response. Alternatively, there could be an excitatory interneuron between the projection neuron and the nociceptor. So here we have the descending pathway from the periaqueductal gray inhibiting the interneuron rather than the projection neuron directly. And finally, in diagram C, here we have an excitatory pathway. But here we're going all the way out through the spinal cord and into the spine. So we're exciting an opioid neuron in the spine, which is inhibitory on the projection neuron. Okay, so beyond the brainstem, the periaqueductal gray, and the peripheral response, we should take a look at the emotional component of pain because those two are not easily separable. It's difficult to disentangle the emotional response from the sensory experience of pain. And as we saw in the neural circuitry, the projections into limbic regions and cortical regions like the anterior cingulate, the prefrontal, and nucleus accumbens. And it's these regions that are exerting top-down control over pain through the emotional the regulation of your emotional response to the pain. So we can have a situation where we are receiving a noxious stimulus, the nociceptors are active, that information is transmitted into the spinal cord, and yet the emotional disturbance or the experience of that pain is not traumatic or agonizing or painful. And so this is the power of distraction, that something as cognitive as attention or attentional bias can reduce pain. So here's some self-report evidence of that. You can see on frame A, we can see attention modulation, pain score, and we're looking at participant ratings for pain intensity and the unpleasantness of the pain. And you can see when the participants were distracted from some unrelated stimulus, they rated the pain less than when they were instructed to attend to the pain. There also seems to be a trend that patients would report the stimulus less unpleasant when they were distracted, although that didn't reach statistical significance. Mood can also have an effect on pain perception, not so much on intensity, but on the unpleasantness of the pain. So you can see when the participant was in a good mood, they rated the pain less unpleasant than when they were in a bad mood. So the overarching idea is that we have descending projections from higher cortical and limbic regions like the frontal cortex and the amygdala, descending into pain control regions like the periaqueductal gray matter, which exerts some control over the pain response in the brainstem. We talked about the different mechanisms by which that is accomplished. And that allows for a cognitive or emotional control over your pain perception. And that's evidenced by the fact that we can reduce pain by distraction, and also note that depression and chronic pain are strongly correlated. Now, that doesn't necessarily mean there's a causal connection, and there's more research to do in that area, but there is a coupling between the emotional awareness of pain and your sensory perception of